So, Assalamualaikum and a very good morning to all. I would like to call upon Dr. Zarin for presenting or sharing her information or ideas or any knowledge about the evaluation measures to all of us. All right. Thank you very much. You may start.
All right. Thank you, Dr. Zahira. Okay. Can you hear me clearly? Because I feel like there's some lagging. Is it okay, Dr. Zahira?
Yes, your sounds clear.
All right. Okay. Then I will start. All right. Okay. Very good morning, everyone. Assalamualaikum. Thanks for joining me for today's session. So basically, today's session, it wouldn't be too long. I would just like to share a little bit on one of the common methods that we use in testing models, which is called the confusion matrix. So today, I'm going to talk about the basic evaluation measures using confusion matrix. Right, so basically for now, during this talk, I will cover 5 things, which is the confusion matrix itself, just a brief definition about what it is. I will talk about classification and then the outcomes of classifications. Then I will mention the evaluation measures as well as explain a little bit on each of the measures. And then I will share with you on how you can interpret the result that you get from the confusion matrix. All right, so whenever you get a data, usually what you do is you would clean the data, you would pre-process it, you would do some kind of like data wrangling and try to build a model out of it, right? So it could be prediction model, classification model, and so forth. However, how do you actually know that your model is working fine? How do you know that it's serving what it's supposed to do? So that's where this confusion matrix would be of help. So confusion matrix, it is also known as an error matrix. It is most commonly used to report the performance of n-class classification model. So you can use for whatever number of classes. So in today's talk, I would give an example for 2-class classification model. So a confusion matrix is basically a table that has 4 different combinations of predicted and actual values, right? So the value that we predicted, whether it's positive or negative, and the actual value for it. Right, so since confusion matrix is mostly used in testing classification model, so let's first talk about what exactly is classification. Right, so if you're working on data, especially if you want to do predictions, you would like your model to be able to guess and classify certain things. So for example, if you can see in this image, there's a mixture of cats and tigers. Okay, let's assume that you are building a model that would be able to predict, if you show a picture, it can tell you whether it is a cat or it is a tiger. Okay, so let's say the question is, which of these are cats? So when you do a classification, because the question is asking about cats, so the cats, we will consider it as positive. Okay, and the tiger or any other animal would be considered as negative. In this problem, we only have 2 types of animals, cat and tiger. That's why it is called a 2-class classification, because you only have 2 different classes. So if you have maybe another animal, 2 more, for example, then it will become 4-class, and the confusion matrix would get a little bit more complicated compared to 2-class classification. Right, so this is basically what a confusion matrix would look like. Okay, so there are 4 outcomes that can happen, either true positive, false negative, false positive, or true negative. Okay, so let's look at each of this one by one to understand what it actually means. Okay, so true positive here, what it means is you predict it as positive and it is true. So you can see here predicted values, you have positive, negative, you have actual values, positive and negative. So if you predict it as positive, so the question is whether it's a cat, right? So you predict it as a cat and it is actually a cat. So it's going to be true positive. Okay, so true positive, positive here is the part where we predict. True here is the actual part. So true positive means you predict positive and it is actually true. Same goes for true negative. So again, negative means you predict it as negative and it is true. So that's why it's called true negative. So predict as negative and it is actually negative. And then we have these other two, false positive and false negative. False positive, it happens whereby you predict as positive. So you look at the second part first. You predict as positive and it is actually false, meaning that it is not true. When you predict it as positive, but it is actually negative. So that is what we call false positive. So in this case, you predict it as a cat, but in actuality, it is a tiger. So we consider this as false positive. False positive is what we call as type 1 error. I will explain further on this error later on. And finally, we have what we call the false negative. Okay, so same way of reading it. So you have negative, you predict it as negative, but in actuality it is false, meaning it is positive. So in this case, you are predicting this cat here as a tiger. Okay, so predict the value, negative, tiger, but in actuality, it is a cat. So it's positive. So this kind of outcome is considered as a type 2 error. Okay, so what does all this mean? True positive, true negative, and so forth, and why do you need to know it? So this is where the basic evaluation measures would matter, right? There are actually several measures that you can look at, but for today's talk, I would only cover 4, which is recall, accuracy, SO, and precision. So let's look at it one by one. Right. First, let's look at recall. So recall basically talks about from all the positive classes, how many were predicted correctly. So in this example here, okay, so you look at this part here, you predict as positive. Okay, so from all the positive that you have, you want to know which one is actually positive. Okay, so sometimes you predict as you have, let's say, 10 positives, but you manage to predict only 7 of it. So your recall wouldn't be too high. So to calculate recall, what you need to do is, this is basically the formula. You have TP, which is true positive, divided by the total of true positive plus false negative. Okay, so look at this part. So these are the actual positive values. Okay, so there are actually 4 cats. So out of 4 cats here, how many that your model managed to predict? Okay, so in this case, we predicted 3. So the model predicted 3 cats. In totality, we have 4 cats. So 3 plus 1. So you look at this row here. So 3 divided by 4, you get 0.75. So in this example here, your recall would be about 75%. So when you have 4 cats, you would be 3 out of the 4. So in order for your model to work well, recall needs to be as high as possible. Next, we have what we call as precision. Okay, so precision talks about the classes that you predict as positive, how many are actually positive. Okay, so recall just now, all positive classes, so you look at the row, right, this part here, how many were predicted correctly. Precision talks about from all positive classes that you predicted, the model predicted, how many are actually positive. So you would look at this column here. Okay, so these are all that your model predicted as positive. So your model predict 5 cats, but in actuality, how many cats are there out of the 5? So the formula would be, you look at true positive, you divide it with true positive plus false positive. So you got 3 here from this part here, 3 cats, and then you get 5, the total of this row. Sorry, the total of this column. So 3 to 5 to 1.6. So meaning that in this model here, this problem here, is only about 60%. So same goes when you're building a model, you would want your recall to be as high as possible, and your precision should also be as high as possible as well, because you would want to be able to correctly predict if the certain item is positive or negative. Next, we talk about accuracy. So if you're building a model, if you're not looking at all those other measures like F score, you would always look at accuracy. So I believe that when you do any research, accuracy is something that you would never miss. Okay, so in this case, accuracy talks about for the whole class, even if you predict it as positive or negative or whatever. So meaning in this whole problem here, how many were predicted correctly? So it doesn't matter whether it's positive or negative, but you want to know out of all that have been predicted, which one is correct. So this would be this diagonal part here. So you would look at only the true positives and the true negatives. So in our case here, you would have 3 true positive, 4 true negatives. So that's in total would be 7. And in this whole problem, there are 10 animals. Okay, so you will get 3 plus 4 over 10 is 0.7. So the accuracy of your model is 0.7. So same goes for accuracy, it should also be as high as possible. So if you look at recall, it's 0.75. If you look at accuracy, it's 0.7. Usually, if your data set is balanced, and then you did proper cleaning and everything, your recall and your accuracy shouldn't be too far off. So in our case here, we got recall 75%, accuracy 70%. So that's correct. Okay, so if you have your accuracy maybe around just 50%, but your recall is very high, 80%, or the other way around, maybe your accuracy is about 85 or 90 and your recall is only about 65%, then you should look at your data set. So maybe there are some imbalances in your data set. Maybe there are, out of these 10 cats, you have 9 cats and one. So, all right, so when you build a model, when you look at the results, the measures and everything, you will be able to tell whether your model is good enough or not. So lastly, out of that 4 measures, the last one would be F measure. So F measure basically compare the impact of recall and precision together. So recall just now, if you remember, talks about positive classes, how many were predicted correctly. precision, from all positives, which one is actually positive? Okay, so if you want to compare between two or more models, you would want to look at either recall or precision. Okay, and recall and precision here, the score wouldn't be too similar. So if you look at, let's say you're comparing model A and model B. So model A has good recall, poor precision, and model B is the other way around. So which of those two models should you select? Right? So it's quite hard to make a comparison like that. That's why we have what we call F measure. So what F measure does is basically giving a harmonic mean between recall and precision, so that you get a score that you can use to compare between different types of models. Okay, so the way to calculate the F measure would be 2 times recall times precision, and then you divide with recall plus precision. Okay, so in our case, recall is 0.75, precision is 0.6, and you would get 0.67. So your F measure would be 0.67, meaning that the harmonic mean between recall and precision is 0.67. So when you do this F measure calculation on other types of model as well, you would be able to compare between your model and existing models to see which work better on the data set that you have, right? So compared to recall, precision, and accuracy just now, F measure is more towards benchmarking and comparing your model with other existing models. Right, so that's basically on confusion metric, the whole table of it, the parts of it, true, positive, true, negative, false, positive, false, negative, and the method on how you can calculate each of the measures that I've mentioned just now. So now that you have all these numbers, 70%, 65, 60, and everything, what does it actually mean? So if you have a confusion matrix and you don't understand what it is, it wouldn't give you much benefit, because nowadays, if you're doing your projects or experiments using Python, confusion matrix is not something that you need to calculate because it can be generated. So if you use Python, for example, you can build a prediction model, and based on your result, you will be able to tell you the score of recall, measures, F-score, and all that. But if you don't understand what the result means, then you wouldn't be able to assess whether your model is good enough or not. So interpreting the result is also important. So let's look at our example just now. So we have accuracy, precision, recall. So accuracy is about 70%, precision 60, and recall 75. So what it actually means is that for accuracy, because it's 70%, it means that if there are 10 cats, 7 will be identified correctly. So depending on the problem that you're having, 70% can already be a good score. But if you're working on critical problems that relates to maybe something life-threatening, medical issues or whatever, then maybe 70% wouldn't be a very good accuracy score. So it depends on your problem as well. So accuracy 70% basically means 10 cats, 7 will be identified correctly. So only 3 would be wrongly identified. For precision, 60%, it means that if you have labeled 10 animals as cats, okay, so this is the model doing its job. So you label 10 animals as cat, only 6 out of 10 that you have labeled is actually a cat. So meaning 6 is correctly labeled, the other 4 is wrongly labeled. So therefore, this is what precision means. And finally, recall. So recall 75%, meaning that if there are 10 cats, the model can only identify 7. Okay, so the other 3 will be missed, right? So again, recall would be if you have 10 cats, model will only identify 7 and it will miss the other 3. So when you build a model, you have all these measures: accuracy, precision, recall, which of course if you can make all 3 measures high score, would be superb. You would have a very, very good model, but that is not always the case. So how do you decide whether you want accuracy more, precision more, or recall more, or whatsoever? How should you decide which one you should give more attention to? So basically, it depends on your problem. Okay, so let's just take precision versus recall. So when you talk about precision, you talk about how sure you are with your true positives. Okay, so if you label something as positive, how sure are you that it is correct? Okay, recall is how sure are you that you're not missing any positives? So which is more important? Do you want to get as many positives as possible, so you don't want to miss any of it, or you don't mind missing, but you want it to be as correct as possible, right? So 2 different scenarios. So if you want it to be correct, you want to get only the positives, you don't want false positive, then you would go for precision. But if you don't mind having missing some positives, then sorry, if you don't want to miss any positive, you don't mind that it's a false positive, then you would go for recall. Okay, so maybe it would be better if we look at an example. Okay, so in the case of spam filtering, if you choose precision, it means that you want to be more confident of your true positives. So in the case of spam, if you talk about precision, you want to be sure it is a spam. If you're not sure whether it's a spam or not, you would rather it being a regular email. Okay? Because if you are doing a spam filtering and you don't really care about precision, then regular emails can also be considered as spam. You're not so sure, right? So precision is low. So you could think that, okay, maybe this kind of email is a spam. So you just put it, but it's actually false. It's a false positive. So if this happens, then a lot of maybe important emails, whatever emails that the user is waiting for, would end up being in the spam box. Of course, it is not good. So when you're doing spam filtering, precision would be much more important. So you need to be extra sure that it is a spam, then only you would put it in the spam box. If you're not sure, then your model should decide to label it as regular mail instead. Okay, so this is for precision. So if you want to be extra sure that it is positive, then precision needs to be very, very high. However, in the case of diagnosing patients for diabetes, cancer, whatever, you would rather have some false positives, okay, so false alarm, you wouldn't mind having false positive in comparison to having false negative. So false positive means that you diagnose someone as having diabetes when he actually do not have diabetes, as compared to you diagnose someone as not having diabetes but actually have diabetes. Okay, so in this case, okay, recall would be much more important because you want to get as many positives as possible, even though it is false. Because if you diagnose someone as having diabetes, when in actuality he doesn't have diabetes, it's fine because he would do follow-up checkup and everything, and eventually we would know that the person, okay, actually it's a false alarm, you don't have diabetes, which is a good news for that patient. But if you diagnose someone as not having diabetes when he actually have, it is unacceptable. So false negative is unacceptable because he would go on living his life normally, thinking that he doesn't have diabetes and so forth, and end up maybe at the hospital feeling much worse, or maybe he can even take his life because he doesn't know that he's having diabetes and he's doing things that a diabetic person shouldn't be doing. Okay, so if this is your scenario, then recall would be the measure that you would want to be having the highest score compared to the other, right? So when we talk about that, the next would be on the errors. So again, type 1 error is when you predict it as positive and it is false. Okay, so it's false positive. Predict as positive, but it's false. So in the case of diabetic just now, when we talk about recall here, false positive is when we say that, okay, you have diabetes, but actually you don't. This is less harmful. Okay, so if in the scenario of diabetes here, having a slightly higher type 1 error would not harm so much. Okay, same goes to like, let's say the bank want to give out loans. So it assess the customers, trying to get customers who are only good customers. So bad customers, maybe the kind of customers that they think wouldn't be able to pay back the loan and everything, they don't want to give it to this kind of customers. So in this case, if it gives wrongly, so it tries to detect the bad customers, but if it detects a good customer as a bad customer, it wouldn't be too harmful. So it will refuse the loan, okay, to them, but this customer would be able to apply again, apply a few times until they finally be considered as good customer and get the loan. Okay, so it is less harmful for the bank, maybe a bit more harmful for the customer because they need to fill in the forms and everything and come back and forth again. And another example would be like maybe if you're saying a person is pregnant when she's not pregnant, also is less harmful compared to saying that the person is not pregnant when she is pregnant. Okay, so type 1 error is basically talking about when you say that it's positive, but it's actually false, right? So we would consider type 1 error as a less harmful error. Type 2 error is when you predict it as negative, but it's actually positive. So type 2 error is false negative. So in the same case as diabetes is now, so if you tell a person that he doesn't have diabetes and he go on living his life normally, he might jeopardize his life. Okay, because he did did not go to the hospital, did not take the medication that he needs. So we would say that this is a much more harmful situation. The impact is much bigger compared to type 1 error. Same goes in the bank scenario just now. So if you wrongly label a good customer as a bad customer in terms of giving out the loans, it is still not that harmful. Maybe it would affect your image a bit, maybe, but still the customer can apply a few more times and the damage can still be restored. Sorry, the damage can still be solved. Maybe talk to the customers and so forth, so that they won't. But for type 2 error, if you label a bad customer as a good customer and you end up giving loans to them, then the damage would be much bigger in terms of cost. Okay, so you might give out loans, I don't know, millions or thousands or whatever to this bad customer that you have wrongly labeled as good. and the bank can lose your money, which in respect to the banks, it would be much more damaging to them, right? So I think this is my last slide. Like I mentioned, it's just a short sharing session just to briefly share on this common evaluation method for classification models. So just a recap, confusion matrix is very, very useful in evaluating your model. But what is important is not just to get the results, right? Not just the recall, not just accuracy, F-score and all that. The numbers, of course, give some indication. But if you just see it as numbers without understanding what it is, then you wouldn't be able to ensure that your model gives optimal solution. All right. So I guess that's basically it for today's session. So even though it's short, I do hope that you managed to get some brief idea on confusion matrix, and maybe it will help you get some ideas on how you can apply it in your research. All right. So that's all. Thank you. I would pass back to the MC, Dr. Zaira, maybe for some question and answer.
Oh, that is a very precise and very good webinar. Thank you for sharing the knowledge. So I would like to call upon the students or staff or any that have any doubts or questions to ask Dr. Zareen regarding on the evaluation methods. You may ask or comments or request for any information about the evaluation to Dr. Zareen. So I hope any of you would like to ask question. Maybe I will check the chat session. Maybe there some of them chatting.
All right.
Yeah. Any of you have a doubt about how to make a classification? What technique to use? Yes, please.
Assalamualaikum. Can I ask?
Salam.
Cik Shah here.
All right.
Okay. My question is usually how we can identify this type 1 and type 2 error in common scenario.
All right. Thank you, Dr. Sharizan. So maybe I go back in the slides. So basically type 1 and type 2 errors is depending on whether it is a false positive or false negative. So in real life scenario, type 1 error would basically mean that you predict something as positive when it's actually negative. Okay, so let's take an example. I think false positive, usually when I talk about false positive and false negative, the best example would be in the medical line because you see the impact even more there. So like the diabetes example just now, so false positive is when you say to a person that, hey, you have diabetes. So the person would be worried. Of course, there are some implications to that person, but that person would go on and visit more doctors, try to get some medications or whatever. And when they know that, oh, okay, actually, after further testing, you don't have positive. Sorry, you don't have diabetes. It is less harmful compared to telling a person that you don't have diabetes when they do. So in this current situation, we okay, with this pandemic and everything, this same goes to that. If let's say we don't do any swab test, whatever, we try to predict a person as having COVID or not having COVID based on certain type of details, maybe based on their location in MySejahtera or whatever, we try to predict whether a person is positive or not. It's much better to have a lot of type 1 errors, which is false positive, compared to having type 2 errors, which is false negative. Because it is much better to tell that you have COVID, quarantine them, and do further checks when they actually don't have COVID. It's much better compared to saying you don't have COVID, it's negative, and then let the person roam around. And after further tests, we found that the person is actually having COVID, right? So when we talk about this, we would say that type 1 error is less harmful compared to type 2. But if have errors, both false positive and false negative is low in numbers, that would be much, much better. Right? So I hope that answers your question, Dr. Sheridan. Are there any other questions?
Good morning, doctor.
Mm-hmm.
Okay, I want to ask if we got some number value from every measure. For example, if we got 0.9,
Okay.
it can be categorized as a good model or a not good model. Is there any limit? For example, there is a range number between 0.8 to 1 is categorized as good. 0.6 to 0.8 is categorized as sufficient or not good. Is there any specific number like that?
All right. Thank you for the question, Marvin. Well, I would say that there are no actual standards saying that, okay, from this range to this range, it is good or it is bad. So basically, for all type of measures, it would be between 0 to 1. So meaning 0% to 100%. So obviously, the higher score that we get, the better. Okay, but like I mentioned before, for because these are when you do the testing, you got different measures. So all measures would have different scores. So you would need to choose which measure is much more important than the other, so that you get a much higher score for that measure. I would say it's quite impossible to get all 4 measures to be very good. And if you do get accuracy, recall, F-score, precision as maybe 90%, then it's not saying that the model is not good, but you might need to look back at your data. Sometimes when you have a very, very good score for your measures, it would signal that your data might be biased or some kind. So too high of a score might also signal some problem. But if you have checked your data is all fine, it is balanced, it has been checked by the experts and everything, but you still have a good score, then that means your model is very, very good. But usually I would say if you are between the range of maybe 70 to 80, that is already considered as good. Right?
Okay, thank you, doctor.
No problem. Is there any more question? Maybe I would like, yep.
Dr. Zarif, I've got one question. If we got one table of confusion matrix, what kind of thing that we want to discuss in the paper? What kind of thing that we want to describe inside this table? Is it we have to mention only about the precision, recall, and F1 measure, or is there anything that we want to focus in this confusion matrix table? What kind of thing to discuss when we write paper?
All right. Thank you, PM Robia. So, okay, if you are writing a paper, okay, let's say you build a model. Okay, quite recently, I did develop a model to try and detect depression. Okay, so I would use a table as well, whereby I would have, well, usually if actually, well, you do actually put the confusion matrix, especially if it's a two-class classification. If it's a four-class, six-class, or more, then maybe you would put it. But if for a two-class, having a table, something like this would be good enough already. So you have the accuracy, precision, and recall. And you would have the percentage, and you would try to interpret the data, discuss the result here, like what I did at the site here. So when you do experiments, usually, even though it's just two class, but you would have different features, for example. So let's say you have A is the basic model. You would compare it with, okay, let's say you have, okay, let's take the depression detection example just now. So you have depressed and non-depressed. So it's a binary class, either yes or no. When you do, you write papers, academic papers and all that, you would not want to just have like one column like this. So basically just one model, and you have the accuracy, precision, and recall. What you would want to have is more than one. Either your model have different features, so you would compare, maybe model A is having one feature, model 2 have two features, model 3 combination of, I don't know, 3 features or something like that. So you would have 3 confusion matrix, one for each model. So you don't display that in your paper. Instead, you display accuracy and then one column for the first model, one column for the second model, one column for the third model. And if you're comparing it to another existing work, for example, you might have another column stating the accuracy, precision, and recall of the other work. So when you have all this, you would be able to interpret the result. So let's say I'm having two models, because I'm doing NLP, so maybe one is using TF-IDF, one is using bag of words. So TF-IDF would have a different accuracy compared to bag of words. Same goes to precision, same goes to recall. Maybe in one, if I'm doing TF-IDF, accuracy is higher compared to bag of words. If I'm looking at precision, maybe bag of words have better precision. So if you're writing a paper, these are the things that you would want to look at. So why is the accuracy higher in TF-IDF, but precision is higher in bag of words? So you would discuss all these matters and try to relate it to your data and the result. Right. So I hope that answers the question.
So in the paper we don't have to put the picture of the confusion matrix. We just show the table, is it?
Yep. But that is my style of writing lah. So if you want to put the confusion metric, it's not wrong. But for me, I would rather, because like I said, if there's more than one model, we would have more than one confusion metric. So rather than putting a lot of confusion metrics there, I would prefer having a table that has summarized everything and discuss it in the discussion section. Right? So not saying it's wrong lah to have the confusion matrix. You can have it, no problem. Right?
So, saya punya ada 8 tu yang saya is it too much ah. 8 classes
Itulah.
tu.
Itulah when you have kata 8 tu kan. So if you feel like having all 8 tu membantu orang untuk lebih faham, it's okay to have it lah. But I would rather translate it in a table and maybe have a graph so that kita terus nampak perbezaan between all that 8 models lah.
Okay, convert into graph. Okay. Thank you.
All right. So is there any more question? Okay, just now I was mentioning before PM Rubia asked the question. I'm not sure. Usually when we talk about confusion metrics, we talk about accuracy, precision, and recall. But there's actually one more measures that is also quite important, but I rarely see people use, which is called specificity. Okay, so maybe if you are working on a model that that wants to look at negative results, then you would use specificity here. So recall just now, I mentioned that it looks at true positive, right? So from all the positive classes, we want to know which is predicted correctly. So we've put high value on the true positives. Okay, so it works when, like for example, in the diabetes case and everything, when you want to have more false positive instead of false negative. But if you're working in a problem or a scenario whereby, for example, you are testing people's urine to see whether it contains drug or not. If it contains drug, you would put them in jail. If it doesn't contain drug, then you will release them. So in this case, maybe you would appreciate more negatives than positive because you don't want to wrongly put people in jail, for example. So if you value true negatives more, then you will have this another measure called specificity. So the formula is almost the same, but instead of TP, you would have TN here, so true negative, divide by true negative plus false positive. So that's just an extra information that I did not put in here because I rarely see people use specificity, but maybe in your work there's some part that you think would be better using this type of measure compared to the presented today. All right. So any more question from the students or fellow lecturers?
Any question?
No question, Kak Zahi.
No more?
No.
All right. Right, so if there's no more question, then I think that's it from me. I'm not sure if the organizing committee, if you have anything to add.
Zahi, sudah boleh close.
I think we should wrap up this webinar. So thank you very much, Dr. Zareen, for sharing your knowledge on this evaluation. It's a very short and precise and very good information. I also would like to share this with my students. So I hope we can close this webinar with tasbih kifarah. Okay, with this, the committee would like to say thank you again to Dr. Zareen. Thank you very much for the informative webinar. Thank you, Zareen.
All right. Thanks as well for inviting.
Yeah.
Thank you, Dr. Zarin. Very good information.
All right. Welcome, everyone.